All right, we're back. We are on page 3 of notes 8 of Calc C. We're talking about alternating series and what we want to talk about now. So we know an alternating series will converge if it alternates, the terms decrease in magnitude, the limit of the terms is 0. So that's the alternating series test, tells you if it converges. If it fails to converge, it's probably going to fail to converge because of part 3 there. The limit won't be 0. In Calc BC, you don't really run into a series where like the limit, where the magnitude of the terms doesn't decrease. Like it doesn't happen very often. So I wouldn't worry about that. It's more the limit being 0 that you should worry about, and that's the first one you should calculate when you have to choose. So we want to talk about the error involved. And error, if you actually, I don't even know if you know it yet. Yeah. Error, Lagrange Era Bound, right? You calculate m, the absolute value of x minus a to the n plus 1 over n plus 1 factorial. It's like kind of looks like the first term left off, but it's not quite the first term left off. It turns out that for alternating series, the error is the first term left off. So what I've done here is I've drawn like a picture of the partial sums. But let me give you a more general idea of what's happening. So say we have a series, right? So this is kind of like independent. You know what I'll do? I'm going to add a page. Add a page. I'm going to add a page somewhere. What page am I on? I'm on this page, right? Yeah. All right. Add page. I'm going to draw a picture. And it's not going to be a great picture because I'm not a great artist, but we have a series, and let's say that this is the actual sum. Now here's what an alternating series does. The first thing you do is, like, let's say the sum is positive, right? So you start and let's say your first term is positive. So there's a lot of caveats here. You start and you approximate it first by just kind of like going to the first term, right? Your first partial sum will go like this far, right? So this is like your first partial sum, so we'll call it like S1. Now, the way that I usually think about this is you're trying to hang a picture, right? And the picture that you're trying to hang, you want to be like perfectly centered on, okay. All right, I mean, that's just disrespectful. That was like clearly, you know, honestly, like I'm not that bad. All right, I guess I am that bad. You're drawing a rectangle. Okay, so you're trying to hang a picture and you want your picture to be perfectly centered, right? So what you do is you get two people and they're gonna hold on to the picture. I'm gonna draw them. I don't want it. I want to draw them. Right, so you got your two people, they're helping you out. Two people, and you're like, nah, all right. So the first thing you do is you're like, move far to the right. And they take your picture and they move it over here. I'm like, guys, way too far, way too far. So then you bring in the next term of the series, you get your next partial sum. So you go back this way, but you overshoot. So now you're here, right? So this is your second partial sum. So that's the first term plus the second term. But now you're all the way over here, right? You were over here, you went too far this way. So what you're gonna do is you're gonna bring in the third term of the series. When you bring in the third term, you're gonna move back over here. And you can kind of get a sense of what's happening is so the magnitude of the terms is decreasing. So like you're never going as far back as you were before, and they have a limit of 0. So if you do this forever, and like I'm not going to, but if you do this forever, you're gonna zero in on the actual sum, which is where you really want to hang your picture, right? So we're here, and then I'll do like a couple more. And maybe you get to here, etc., right? So you just keep going back and forth and back and forth and back and forth, and eventually you get to the true sum. The most you could possibly be wrong when you're done hanging it is by the next term, right? Because the next term, if I had stopped here, the next thing I would have done is gone this far. I would have overshot, but I definitely overshoot by less than like the true value. The most you can be wrong is the absolute value of the first term you left off, because everything after that is just gonna like zero in smaller. So if we had stopped here, the most we could have been wrong would have been this, because everything after that just zeroes in because the magnitude of the terms is going to 0. So that's it. That's how you find error. It's the magnitude of the first term you left off. And it's super easy to find, right? So you might remember Lagrange Era Bound. I already mentioned it in this video. Pain in the neck. You got to find the n plus first derivative, take its absolute value, You got to look at it on the interval from like A to the center, or the center to the value, and then like where's it a maximum? Giant pain in the neck. Alternating series, not a pain in the neck at all. You kind of actually hope that it's going to happen. So the maximum error is the absolute value of the n plus first term, just the first term that you leave off when you do these things. So let's see if we can do it. So you just basically hope, right? And if a problem wants you to use Lagrange, it'll almost always say use Lagrange Era Bound. Otherwise, hope that it's alternating, use alternating. So use a calculator to approximate the sum of the series using the 40th partial sum, estimate the error. All right, so the 40th partial sum, I'm gonna call S sub 40 for some reason, is gonna be the sum from 1 to 40 of -1 to the n plus 1 over n to the 4th. And then that's definitely a calculator thing. Now, this is a series that alternates, terms decrease in magnitude, and the limit as n approaches infinity of 1 over n to the 4th is 0. Therefore, the series converges by the alternating series test. So it's important, personally, I think it's important that you show that the series converges, because if it doesn't converge, then like you can't really find the error because it doesn't converge to anything. Converges by alternating series test. The maximum error is going to be the first term left off. So if the last term we get is by plugging in 40, the first term left off is when we plug in 41. The maximum error is going to be, it's less than 1 over 41 to the 4th, because we used up to 40. So I mean, I can use a calculator to get these values. They're probably like vanishingly small. Let's see. Share calculator. Got this. So if I want to do the sum, so I know it converges. So now it's just a question of like, how close do I want to get? -1 to the n plus 1, and then n to the 4th. So it's really small. And then 1 over 41 is incredibly small. So that's like how wrong you could be. So like the true value is somewhere in between this minus this and plus. So the actual value is somewhere in this interval. So if we get, you can get closer, right? So like say we did 80. So here, now the error would be the first term left off, which is going to be 81 to the 4th. It's like incredibly small, right? So then the true value is between this and, I don't even know if this is going to change the decimal. Might not. And that, it's somewhere in between those. So if you had to guess, 0.947033, pretty good guess. All right, let's go back to the notes, see what else is on this page. There's only one more problem, so let's do it. All right, so error, alternating series, error term, first term left off, best thing in the world. Like you always just hope that it's alternating. Approximate the value of cosine of 1/3 using the first 3 terms of the Maclaurin series for cosine. Find a bound on the error in your approximation without using Lagrange Era Bound. All right, so without using Lagrange Era Bound. So it should just be the first term left off if this is a convergent alternating series. So cosine of x, I always like to start with this just so I like don't mess up. Mostly you just don't want to mess up. It doesn't really matter what you're doing. First 3 terms. All right, so I'm going to go one more. So, and I'm going to say this approximate because it's not equal. That's like, I make that mistake all the time in these videos, and I go back and I fix it, but I hope it's not like messing anybody up. So the cosine of 1/3 is approximately 1 minus, I'm just going to do, well, let's do this. 1 over 2 factorial, 1 over 3 squared plus 1 over 4 factorial, 1 over 3 to the 4th. So it's approximately that. Okay. So now, how do I establish that this is convergent? I mean, first of all, the series for cosine converges for all x, so like it definitely converges. But I'm going to say the sum from 0 to infinity of -1 to the n 2n factorial 3 to the 2n. So this is cosine. I basically just took the nth term and I plugged in 1/3. So the nth term is -1 to the n, x to the 2n over 2n factorial. Plug in 1/3. So there is like a 1. Technically, there's like a 1 to the 2n here. But why would you write that? I'm going to say alternate has terms that decrease in magnitude. Oh my God. No one could say that that says magnitude. M-A-G. Limit as n approaches infinity of 1 over 2n fact. I've never been so sure about a limit being 0. Like 1 divided by this beast. 0, therefore, converges by AST. Therefore, error is less than the first term left off. So the first term left off is, oh, you're not my highlighter, my laser pointer. First term left off is this term. So the error is at most 1 over 6 factorial, 1/3 to the 6th. That's the biggest the error could possibly be. We could have used Lagrange because this is a Taylor polynomial, but it said to basically not use Lagrange. So hope that it's alternating. It is. It's convergent alternating series. We use the alternating series error. Perfect. All right. I'm going to stop this here, come back in the next one, and do some more. So I will see you there.